Welcome to our presentation on deformable NeRF using recursively subdivided tetrahedra. In the following sections, we'll explore our goals, examine existing challenges, detail our DeformRF method, and review our experimental results. Let's begin. While neural radiance fields, NeRF, have shown promise in novel view synthesis, their implicit representation limits explicit control over object manipulation. In this paper, we aim to seamlessly integrate the manipulability of tetrahedral meshes with the high-quality rendering capabilities of feature grid representations. This integration facilitates the application of user-directed control and supports rigged animations in NeRF, enabling the production of high-quality rendered animations tailored to user specifications. Researchers have proposed integrating explicit geometric proxies to enable deformation. However, these approaches face two main challenges. Firstly, they require a time-consuming and computationally intensive process of surface extraction and tetrahedralization for each object. Secondly, this process becomes particularly challenging for objects with complex topology or those containing thin structures, as it tends to result in one of two scenarios. In one scenario, to accurately conform to the object's intricate details, an excessive quantity of small tetrahedra is generated, significantly increasing the storage overhead. Alternatively, limiting the total number of tetrahedra often results in the creation of poor-quality tetrahedra, which adversely affects the efficacy of deformation tasks. In this paper, we introduce a novel method, termed DeformRF. Departing from traditional practices, we propose a two-stage training framework, which offers a one-time solution for tetrahedralization and avoids the time-consuming marching cube process for surface mesh extraction. Furthermore, we introduce the concept of recursively subdivided tetrahedra, which virtually generates detailed meshes without the necessity to store these subdivisions. This enables multi-resolution feature encoding for tetrahedral mesh, resulting in high-quality rendering capability. We propose a two-stage training strategy to avoid ill-shaped tetrahedra and tetrahedralization for each object. Starting with an almost regular tetrahedral grid, our model initially retains key tetrahedra surrounding the object and subsequently refines object details using finer granularity mesh in the second stage. In order to fully harness the advantages of feature grid methods in rendering while effectively integrating with tetrahedral structures, we propose multi-resolution tetrahedral representation together with hierarchical barycentric inference. The barycentric coordinates of the sampling point in the coarse tetrahedral mesh can be easily computed. We propose an iterative approach named hierarchical barycentric inference that allows us to determine which of the 8 child tetrahedra at level L+1 contains a specific sampling point at level L, using the barycentric coordinates of the point in the parent tetrahedron. Moreover, the barycentric coordinates of the sampling point at level L+1 can be explicitly calculated from its coordinates at level L, using a closed-form formula. Please refer to supplementary materials for more details. After the vertex identification and barycentric calculations process, we successfully extract the features of the sampling point at the given level. By iteratively employing hierarchical barycentric inference coupled with barycentric interpolation, we are able to obtain features across all hierarchical levels. Subsequently, these features, derived from different levels of the tetrahedral mesh, are concatenated to form a comprehensive feature vector for the sample point. We quantitatively compared various state-of-the-art methods on the synthetic NeRF dataset and the Tanks and Temples dataset. To further demonstrate our method's capabilities, we have prepared several demonstrative experiments. The 4 videos on the left showcase the rendering outcomes of objects as they deform upon impacting a plane under the influence of gravity. The video on the right displays the rendering results of an object deformed through user manipulation. We have also simulated the deformation and rendering of objects under compression by different planes. It is evident that our model supports these simulations while maintaining high-quality rendering. The rendering results of the rigged animations are presented here. Our method successfully supports animations driven by skeletal structures, and under the designed poses, the rendering remains photorealistic. Thanks for watching.